Hey guys, now this is something new we didn't talk about before. So I'm just you can kind of think of this as a flipped classroom. I'm teaching it in the video. It's called the central limit theorem. So many of us have been asking, okay, we know that we can save time and money and energy. Instead of asking the whole population, we can just ask a sample. But how big does our sample need to be? All right. We also been kind of scratching our head and asking questions in class. What if our sample, or excuse me, what if our population distribution is skewed? Well, then what would our sample be exactly? Well, the answer to this question is if we ask a quantitative question, if we take many, many samples from a skewed, we're continuing to take an average. So we'll actually, once we take 30 or about 30, my sample from this red distribution, the sample will actually end up being normal as long as I make sure my sample size is 30 or greater, okay? So regardless of shape, what we learn, and we'll do an activity in class to also prove this, we won't just take this for granted, but even if our population distribution is skewed, our samples won't, because our samples will be the averages. And so I'm just graphing averages, and the average has to arrive at whatever the average was here, my samples have to arrive at that same average, plus or minus a little bit. And whatever my average is here, my samples would have to arrive at that same average, as long as I take a large enough sample. So let's take a look. It says, when a population is normally distributed, we know that the sampling distribution of X star will also be normally distributed. So if I took a sample from a population, for instance, height, right? That's normally distributed. And I took a sample, we know it's going to get narrower, but it's going to keep that like shape normally distributed. This concept is illustrated by this picture. Take a sample, it gets narrower, but if it's bell-shaped and symmetrical, it's still bell-shaped and symmetrical. However, most population distributions are not normally distributed. If our sampling distribution is skewed or not normal in some way, we cannot use normal calculations to answer questions. Thankfully, a pretty remarkable fact about sample means helps us out. When the sample size n is large, then the shape of the sampling distribution, so when the sample size is large, the shape of the sampling distribution will be approximately normal, regardless of the shape. So that's what this is saying. If it's skewed, my sample size would still be normal. If it's skewed the other way, my sample size will still be normal, as long as my sample size is large. This makes it very handy. For our purposes, we'll define large enough to be at least 30. We can be safe in assuming that the sampling distribution of X bar will be approximately normal, and we can go ahead and proceed with normal calculations. So let's do that in question number 37. It says the blood cholesterol level of adult men has a mean of 188 milligrams per DL, whatever that is, and a standard deviation of 41 milligrams per DL. An SRS of 250 men is selected, and a mean cholesterol is found in the sample. Sketch the sampling distribution of X bar and calculate the probability that the sample mean will be greater than 193. Now, we don't say that the sample will be greater than 193. We're saying that the sample mean will be greater. So I don't want to look at this chart of my population distribution. I'm being asked to look at this chart, my sample distribution. All right. So it doesn't say the shape of this data. There's nothing in here that says the shape of the data, but it does say my sample size is 250. So since 250 is greater than or equal to 30, we can say that the sampling distribution is approximately normal. All right? And we said that whatever mu is, that mu x bar would be the same, and we're told that the mean is 188, right? And sigma, well, we're told that sigma is actually equal to 41, but sigma x bar would equal to sigma of the population over the square root of n. So this would mean this would be 41, and we know this would have to be much narrower, 41 over the square root of 250. So this would make the standard deviation 2.593. That's much narrower than 41 because this is such a large number. So sketch a picture of our sampling distribution. We know it centers at the same number, 188, but we know the standard deviation is actually much narrower, 2.593. Now they're asking, what would be the likelihood of it being greater than 193? So I want to find 193 on my number line and go to the right because they said the word greater. So this would be norm, CDF, lower bound, upper bound, mean, and standard deviation. The lower bound is 193. The upper bound is a really big number. The mean is 188. And the standard deviation is not 41 because they asked for the sample mean. So it's 2.593. Now, if we're at home without our calculator, we can open a norm Cdf calculator. Right? And a couple of choices here. I'm just looking for maybe one that I like. Have we used that one before? Okay, so the population mean is, we said 188. The population standard deviation is, oh, we don't want to put that in though. We want to put the other one in. So 2.593. Our lower bound is 193. Upper bound is really big number. Let's go ahead and calculate. We get 0.0269. So this area under the curve is around 3%. So it says, what's that probability? That's our answer. That's the probability. Thanks for joining us, guys. See you next time.